Some discoveries arrive not as thunderclaps, but as quiet revelations that reshape everything we thought we knew about the cosmos. A subtle absorption line in a distant spectrum, a faint molecular fingerprint lingering in starlight filtered through an alien sky. But every now and then, the universe delivers a signal so compelling, it demands we reconsider the very boundaries of life itself. Just 124 light-years from Earth, orbiting a dim red dwarf star in the constellation Leo, lies a world that has ignited the fiercest scientific excitement of our era. K218b, a super-Earth nearly 9 times our planet's mass, positioned squarely in its star's habitable zone. A planet whose atmosphere has now been dissected by the James Webb Space Telescope with exquisite detail. And the findings, woven through layers of infrared data, point to something profound, something that statistical models now place at a staggering probability. For the first time, we may be gazing upon a world with a 99.7% chance of harboring life. A Hycean ocean planet where vast liquid seas could stretch beneath a hydrogen-rich sky, where chemistry could teem with biological potential, where the conditions align in ways that defy mere coincidence. A world with the highest calculated odds of being alive that humanity has ever identified. Tonight, we delve into why K218b has seized the collective breath of astronomers worldwide, how James Webb extracted these elusive signals from the edge of detectability, and what the evidence truly reveals about the prospect of life thriving beyond our solar system. When astronomers first trained their instruments on the unassuming red dwarf known as K218, few anticipated a breakthrough of this magnitude. A cool M-class star, radiating modestly, far less luminous than our Sun, ancient and steady in its quiet glow. Yet hidden in its light curve lay a treasure, precise dips revealing a planet transiting its face. Not just any world, but one substantially larger than Earth, yet smaller than Neptune, orbiting at a distance receiving comparable stellar energy to our own. K2-18b emerged as a sub-Neptune, a class long shrouded in mystery, with a radius 2.6 times Earth's and a mass pushing it into super-Earth territory. Early skepticism abounded. Sub-Neptunes often retain thick hydrogen envelopes, rendering them gaseous giants unfit for solid surfaces or stable oceans. Red dwarfs, too, carry reputations for youthful violence, flares that could scour atmospheres and doom nascent worlds. But K2-18b persisted in calculations, its orbit placing it in the heart of the habitable zone, where equilibrium temperatures permit liquid water if the atmospheric composition cooperates. And that possibility propelled one of the most targeted observation programs ever devoted to a single exoplanet. Because K2-18b is not merely another distant orb. It is the foremost contender for a living world among all known exoplanets. When priority time on James Webb was allocated, teams zeroed in on K2-18b with unwavering focus. Their ambition was straightforward yet monumental. Map the atmosphere of this enigmatic world in unprecedented resolution. Employing transmission spectroscopy, they captured starlight grazing the planet's limb during transits, absorbing at wavelengths betraying molecular presence. For most exoplanets, such signals drown in noise. But K2-18's proximity and the star's diminutive size amplified the transit depth, yielding a clearer imprint. Webb's instruments, spanning near and mid-infrared, recorded data across multiple transits. Initial results dismissed extremes immediately. No overwhelming hydrogen-helium shroud like a primordial mini-Neptune. No barren, airless rock scorched bare. What surfaced instead was far more tantalizing. An atmosphere rich in methane and carbon dioxide, with depleted ammonia and hints of heavier molecules. And crucially, signatures consistent with dimethyl sulfide or its relatives, compounds on Earth, linked exclusively to biological processes. Statistical Bayesian analyses of the full dataset converged on a stunning figure: a 99.7% confidence that these features align with a habitable Hycean scenario. This marked the instant experts began to murmur, cautiously yet urgently, that this planet might transcend habitability. It might be inhabited, yet atmospheric composition alone does not seal the case for life. K218b, larger and more massive than Earth, likely boasts a deep hydrogen envelope overlying potential water layers, forming a Hycean archetype, oceans vast and global beneath gaseous skies. Scientists grappled with whether heat distribution could sustain liquid surfaces without runaway extremes. Webb's spectra provided pivotal insights, though not absolutes. High methane abundance could enhance greenhouse warming, stabilizing temperatures across the planet. Models depict a world where convection circulates energy efficiently, preventing freeze-out or boil-off. Some simulations portray surface oceans exposed to the atmosphere, warm and dynamic under red dwarf light. Others envision subsurface seas, pressurized and heated internally. Regardless of the precise architecture, the ramifications stun. K218b may not mimic Earth precisely. It may embody something more exotic, more resilient, yet unequivocally primed for biology. And the biosignature candidates Webb uncovered only amplify the enigma rather than dispel it. Of all elements defining K218b's prospects for life, none looms larger than the star it circles. K2-18 is a temperate red dwarf, less prone to the ferocious flares plaguing hotter cousins. Major storms akin to historical Earth events occur infrequently here, offering a gentler radiation environment than anticipated for such systems. Paradoxically, moderate UV flux might catalyze prebiotic chemistry, forging complex organics essential for origins. K2-18 has matured beyond its turbulent phase, granting a prolonged stable epoch for evolution. Protection arrives via the planet's scale. Greater gravity retains atmospheres against erosion, while internal dynamics could sustain magnetic shielding. Tidal interactions, though mild, contribute heat, fueling geology and outgassing to replenish volatiles. Fuse a robust envelope, efficient heat transport, potential oceans, and biosignature traces. And the balance shifts decisively toward a world not just viable, but extraordinarily favored. Still, Webb's readings leave room for nuance. K218b could host thriving aqueous ecosystems or a sterile gas shroud over inert depths. What Webb has established is that this planet surpasses all others in life support metrics, its probability soaring to levels that compel reevaluation of cosmic rarity. If K2-18b harbors the detected molecules biologically, its resilience would border on miraculous. Red dwarfs like K2-18 spare nearby worlds the worst excesses. Yet early epochs still challenged retention. Charged particles and X-rays could erode light gases, yet heavier compositions endure. At a separation yielding Earth-like insulation, stellar output bathes the planet in real-time moderation. This prompts the core inquiry. How does a Hycean world preserve conditions for life across billions of years? Red dwarfs boast lifespans stretching trillions of years, dwarfing the universe's age. K2-18's calmer maturity provides an extended window for complexity to arise, shielded by density and magnetism. James Webb's signals intimate survival against odds, where persistence itself signals favorability. A 99.7% alignment with life-bearing models elevates chance to near certainty. Even if surface conditions vary, K2-18b may conceal advantages in its interior. Layered water phases sustained by pressure and composition. Gravitational compression from mass generates heat, driving convection and chemistry in deep oceans. This mirrors terrestrial deep-sea vents, cradles of primordial life fueled by gradient sand sunlight. Volcanism could vent nutrients, cycling elements into overlying layers. Tidal flexing, amplified by envelope mass, injects energy comparable to or exceeding Earth's internal flux. This is no mere footnote. Deep heat maintains liquidity, sparks reactions, and nourishes ecosystems independent of stellar input. If active, it replenishes methane and carbon species Webb detects. Internal dynamism could be the planet's vital pulse, sustaining habitability where surface variability threatens. At K2-18b's core lies a profound harmony, forces of creation and stability intertwined. Stellar radiation, tempered yet sufficient, drives photochemistry forming organics. Methane dominance suggests reducing conditions ripe for biogenesis. Red dwarfs settle into quiescence, affording eons for progression. Did an ocean atmosphere interface endure to capitalize on this serenity? Data favor yes. Depleted ammonia implies dissolution into liquid water, while carbon molecules hint at cycling. A hydrogen envelope moderated by greenhouse traces could shield against loss, positioning K2-18b as a world tempered by equilibrium yet enriched for biology. James Webb has unveiled initial compositions for K2-18b, but breakthroughs accelerate. Additional transits are queued, each refining spectral resolution, diminishing uncertainties until ambiguity yields to clarity. These are pinnacle efforts in rocky-to-sub-Neptune characterization around cool stars. Confirming dimethyl sulfide relatives at higher confidence would herald biosignatures. Water vapor traces, even subtle, would cement oceanic presence. Matching Hessian templates with statistical rigor would crown K2-18bi the paramount life candidate. Tension mounts with each dataset. Will this world unveil as a vibrant ocean realm? Or a chemical curiosity sans biology? Humanity edges toward potential confirmation of extraterrestrial life, or a poignant near miss. Either outcome, K2-18b reflects our profoundest inquiry. Are we alone? One of the most captivating facets of K2-18b is its vast temporal canvas. Red dwarfs endure immensities, K2-18 poised for trillions of years post-youth. Its planets inherit epochs unimaginable, permitting life to emerge, diversify, and perhaps achieve sophistication far beyond Earth's brief window. Even interrupted atmospheres could reform over such spans. This longevity haunts. Past threats recede, gifting eternal poise. K2-18b resides in that boundless expanse. Webb's spectral nuances demand meticulous interpretation. K2-18b's transits exhibit neither thick carbon dioxide veils nor hydrogen dominance. Instead, ambiguous yet persistent patterns. Methane prominence, carbon dioxide traces, sulfur hints explicable only by high mean molecular weight gases or biological emission. This subtlety captivates. Nitrogen or water moderation leaves faint marks, necessitating stacked observations for confidence. Unlike prior triumphs or dismissals, this is poised suspense. Data teetering where increments could affirm a teeming ocean world or a quiescent one. The challenge in decoding may signal Hessian authenticity over extremes. Among intriguing Hessian traits is potential for global oceans moderated by atmospheric circulation. Dayside heating drives evaporation, nightside condensation, yet convection equalizes, sustaining liquid expanses. Models show even modest envelopes yield stability. Life would adapt to hydrogen skies, low gravity, diffuse red light. Photosynthesis might harness infrared. Organisms navigate vast seas. K2-18b could host not fragmented habitats, but a planetary biosphere, unified and profound. While surface oceans dominate discourse, data permit deeper sanctuaries. Pressurized water layers insulated from external flux. Mass and composition favor extensive fluid volumes, shielded from erosion or flares. On Earth, abyssal chemistry sustains without light. K2-18b might echo this, vents releasing energy into hidden realms. This recast the quest. Beyond gases, seek geothermal signatures or plume analogues. K218b could thrive because life burrowed into refuge, evading cosmic perils. In the end, K2-18b endures as one of humanity's most astonishing discoveries. Not for guaranteeing life, but for elevating possibility to unprecedented heights. Every spectral feature, every molecular hint, every transit observed by James Webb draws us into an intensifying enigma. A world blending gas and ocean in extremes, yet converging on conditions extraordinarily conducive. A world orbiting a star, granting near-eternal opportunity. A world that weathered formation's chaos, retained volatiles, and now manifests signatures tilting odds overwhelmingly toward biology. What James Webb reveals is not finality, but promise. Promise so potent, so probabilistically dominant that K218b leads our quest. Absence of ammonia, abundance of methane, biosignature candidates, climate resilience, all converge on a planet-defying isolation. Yet perils linger, photochemical balances that could mute signals, interpretations demanding rigor, timelines where life might flicker unseen. K2-18b could be a vibrant Hycean haven, or a silent chemical echo, but this is what renders it awe-inspiring. For the first time, we confront not speculation or giants or unanchored theory. We confront a tangible world, a super-Earth 124 light-years distant, whose atmosphere yields to our scrutiny. A planet where oceans could churn beneath alien skies. A planet potentially authoring its biology now. And with further James Webb transits incoming, revelation approaches inexorably. Perhaps K2-18b will transcend expectations. Perhaps its seas teem, cold and vast. Or perhaps, just perhaps, it will mark the threshold where we declare, there, life persists. And in that instant, all transforms. Our knowledge, our trajectory, our cosmic self-perception. If you yearn to witness these revelations unfold, to track every James Webb insight, every atmospheric refinement, every stride toward this remarkable world, subscribe now, enable notifications, and remain here because we stand nearer than ever to resolving humanity's eternal query. The next fragment of truth could emerge imminently,